Okay, we're going to continue on here, chapter 10. And in chapter 10, we're talking about obviously solutions. And we're talking about at the beginning, really the idea of like dissolves like. And again, that's the idea that when molecules sort of interact with one another, they are going to be really soluble if they are sort of if they use the same type of intermolecular forces. So if you kind of bring two molecules together that are using really the same type of intermolecular forces as they use with themselves, that will allow them really to interact with one another very easily and will really make them be soluble in one another. When you come together with people and substances that are using different types of intermolecular forces, they do struggle and end up with really the inability to interact with one another over a long period of time. So, we're talking about things like the ability to hydrogen bond, dipole-dipole interaction, dispersion forces. And that means that, typically speaking, ionic guys and polar guys, as we talked about, are going to usually be soluble in each other because they have really an easy way to interact with one another through that ion dipole interaction uh, that really works really well together. Polar things are typically going to be soluble in each other as well. Again, they will either use sort of hydrogen bonding for both of them. They'll use dipole-dipole interaction, and they'll make it really soluble. Also, nonpolar things and nonpolar things are going to be soluble in each other. Again, they are both going to be pretty much using dispersion forces as their way of interacting. It's going to make them really soluble. So these sort of combinations are typically the things that you would expect if you mix them together to be soluble in each other. Insoluble, really, as we talked about, is sort of when you cross over that kind of a polar and nonpolar sort of interaction that's going to occur. And that is going to where you're going to get in some trouble and things are not going to mix. We talked about sort of the limit of solubility that it is based on, for example, like a solid, a lot of times in a liquid, the solubility is based off of temperature. At a certain temperature, you could get a certain amount to dissolve. If you increase the temperature, usually will increase the solubility of a solid in a liquid, and vice versa as well. If you decrease the temperature, typically you'll kind of decrease the solubility of a solid in a liquid. We got into saturated solutions, unsaturated solutions, and supersaturated solutions as well. And again, these are sort of different types of ways you can describe a solution. A saturated solution is a solution where you pretty much have hit the maximum amount of solute that will dissolve in that solvent at that given temperature. An unsaturated solution is one that hasn't really hit that point yet, which means if you go take some solutes to dissolve in it, it should continue to dissolve in that liquid, and it should dissolve until it hits a saturated solution. And lastly, a supersaturated solution, as we talked about, is one where essentially you have way too much sort of solute dissolved in the solvent. And it's really sort of a very unstable solution in a lot of situations. As we talked about, it allows, for really the solid to come out of that solution with very little effort. Just you can knock it, you can add just a little bit more of the solute to it, it'll cause it to really go out. Usually, again, you make a supersaturated solution by making a saturated solution, kind of heating it up, which again allows you to dissolve a lot more of the solute than you would at sort of room temperature. And then when you cool it back down, the solubility of that solution changes. But at that point, you've already dissolved all that solid in it. And again, that's what sort of makes it a supersaturated solution. Questions on that there? So we got into at the very end as well concentrations, and some of this concentrations we've talked about previously, and we've done these examples previously, but we're just going to go through them again just to make sure. Again, a reminder that percent mass to mass, which is what we see in this problem, is the mass of the solute divided by the mass of the solution times 100%. And there's one of those percent concentrations that we talked about as well. And in this problem here, the 2.5 grams of calcium chloride was our solute. The water here is our solvent, which makes up the solution. So a reminder, as we talked about the first time we went through this problem here, 2.5 grams of calcium chloride is our solute, and the mass of our solvent would be our 50.0 grams of water. And that means when we would calculate this, we would take our 2.5 grams. We want to make sure, as we talked about before, that we do add both of these guys together. That is going to give us our total solution and times it by 100%. So again, 2.5 divided by 50 plus 2.5 times 100. Going to give us 4.76% mass to mass, in this case of calcium chloride. Questions on that calculation? So again, we saw it earlier in a previous sort of lecture. Again, it is sort of officially in this chapter, and you might need to use it obviously along the way. We also talked about when you're doing these sort of percent concentration type of problems and you're given a percent concentration, for example, you can turn it into a conversion factor. So again, if it's 37.2% by mass HCl, what that means, again, as we talked about, is that there are 37.2 grams of HCl over 100 grams of solution. Or you could use that in the sort of opposite way as a conversion factor, 100 grams of solution and 37.2 grams of HCl. So in this case, we're actually looking for how much HCl there is and 35.5 grams of the solution. So as we talked about, I think the first time we went through this problem, we want to make sure, it's maybe easier to do it more as a dimensional analysis conversion type problem where you kind of use this conversion. And again, you could just think about units canceling. So we want the grams of solution to cancel and our 37.2 grams of HCl. Again, our grams of solution would cancel in this case. And that would give us our answer here of 13.2 grams. Again, the benefit of this is you don't necessarily have to maybe remember the equation. You could just, again, take it as like, I want to get rid of certain units, and you don't have to remember perhaps, all of the equation here. But again, you could obviously, as we talked about the first time around, you could just plug and chug obviously into this equation and solve for it, which obviously is the same exact math obviously that we did down here, as you would have this guy and that guy, and just solve for that guy. Any questions on percent mass to mass? It's summer school, so we didn't talk about it that much long ago, I suppose. Another really important sort of concentration unit that we covered earlier as well, and that we definitely will see here in the last part of this chapter, is molality. And molality is used in a lot of colligative properties formulas, and it is something, again, that we'll see here in just a second. Molality, remember, is abbreviated with a lowercase m, and not to be confused with, molarity, which is capital M, which is moles per liter. So molality actually is moles per kilogram of solvent. So that is moles per kilogram of just the solvent, not the solution. And this technically is moles of solute over liters of solution, and that is moles of solute over kilograms of solvent. It is a value that is used, like I said, a lot here in colligative properties that we're going to see here in just a second. As I might have mentioned as well, to kind of go between these two, density is typically what you need to kind of go between molarity and molality. But again, you don't want to confuse it. And you don't want to, in a problem that is sort of solution based, when you look at the little m, think mass or anything like that. Again, that is the symbol for molality. So we do approach it kind of a similar way here. If we wanted to calculate the molality like we saw, we want the moles per kilogram of solvent. And obviously we have the grams of our solute here, which is our 61.7 grams of C3H7OH. So in order to convert our grams into moles, we would need to go to the periodic table. And we got 3 times our 12.01 for our carbons, plus 8 actually hydrogens there, 1.008 grams per mole for our hydrogens. And we got 1 oxygen at 16 grams per mole. And that will give us a molar mass here. I punched the number in right. That might be better. 1.008. Try that. Plus a 16. Looks like a 6009. So using that as a conversion factor, 6009 grams per mole. Gives us 1.027 moles. We do need kilograms of our solvent. Here we are given the volume and the density. And since density is mass divided by volume, the mass would be volume times the density, which means in this case 175 milliliters of water times the density of water, which is 1 gram per milliliter, will give me 175 grams of water. It does need to be in kilograms here for our molality, so we do need to do that conversion. And again, there are 1,000 grams in a kilogram, and that gives us 0.175 kilograms of water, which again is our solvent. And now we can solve for our molality, which would be our 1.027 moles divided by our 0.175 kilograms. That gives us something like 5.87. And once again, the units here do not cancel out like molarity. So as we talked about, you can leave it as moles per kilogram, or just like molarity, 5.87, and you can use the little m as sort of the symbol. Similar to molarity, sometimes it's a good idea to if you are using it sort of in a problem, get rid of the little m and you show both of those units, the moles and the kilograms. So again, you don't miss out on where one of those units may be. And you don't think about some other weird unit by just having the little m there. Any questions on molality? Definitely, we're going to see it here in just a second. And some of these colligative properties, there are a number of formulas has molality. The last sort of review here of some of the concentration units that we talked about is mole fraction, and mole fraction is also in some of the colligative properties type of situation. Mole fraction is usually abbreviated with the X, and on the bottom there is whatever the mole fraction is for. But basically, you take the moles, for example, here we'll call this A. You would take the moles of A divided by the total moles, and once again, that will give you your mole fraction. It is, for all intents purposes, sort of like a percentage, but we do not multiply it by 100 to make it a percentage. So the maximum you could have when you add up all the mole fractions is 1, which would represent basically 100% of whatever you're adding together. And again, so you'll get up something like a 0.52 or something like that, which is basically 52%. So we want to calculate, for example, here, like another one here that we did earlier on, mole fraction of methyl alcohol in a solution is composed of methyl alcohol and ethanol. So really, our mole fractions of methanol would equal the moles of the methanol divided by the total moles, which means obviously we need to add the total moles. So 0.328 moles plus 0.929 moles. And that will give us our total moles here in this particular case of 1.257 moles. So our total moles. So to calculate what we're looking for, we take the moles of our methanol in this particular case, divided by the total moles. And in this case, we will end up with about 0.261. About 26% of it is made up of methanol. If we wanted the mole fraction for the other component, we could do the exact same calculation for the other component, which would be our moles of the other component divided by the total moles of 1.257. And here, 2.5 seconds. There we go. We'll end up with 0.739, or about 74% of it is the other one. We also could have got that after we got this guy by simply taking 1 minus 0.261, as 1 would represent 100% of what is there as well. So we could have done that as well. So we see mole fraction in a couple of places. We saw it earlier when we were doing, obviously, gas laws, and when you do not have enough information, for example, to put it into the ideal gas law, but you do have enough information to get the moles of everybody, that is where you can use the mole fraction. And again, we'll see it here in some colligative properties in just a second as well. Remember that if the moles are not given to you, but you are given things in grams, you could use the molar mass from the periodic table to convert them to moles, and then you have the moles of everything. So that is, again, something commonly that you need to do. Any question on mole fractions? And obviously, not to be left out, obviously, the granddaddy of all, which is molarity, which is our capital M moles of solute per liter of solution, which we use in a number of places, and obviously does come into play a little bit. Remember that you can think of it as a formula, and again, you can rearrange it like we did with a number of that solution stoichiometry situations where we needed to solve for any of these three things. Again, when you're using molarity in a calculation, as we talked about, also probably convert it into those 2 units. So this brings us to sort of the last sort of thing we're going to talk about here about solutions, which is colligative properties. And colligative properties really depends on the number of particles that are dissolved in the solution. So the presence of particles in solutions has a great effect on normal sort of processes that a solvent, for example, could go through. So what do I mean by that? I mean that if you had, say, just water by itself, just plain old water here, under normal situations, if you just had water and you wanted to, say, boil it, for example, put a little fire under it, the water molecules, right, will gain enough energy, and eventually, right, they will be able to kind of work their way to the surface, and it will start to boil at that point, right? Or if you wanted to freeze this guy, right, at some point you would cool it down, remove some energy. These guys would just, find each other, kind of come together and start to freeze. Now, the idea of whenever you sort of put any type of particle into a solvent to make a solution, which is essentially how you make a solution, right? A solution is really, again, 2 parts, the solute and the solvent, right? So when you kind of put those 2 guys together, the solute, which is typically what's dissolved in there, you actually change sort of the components of the solvent, and things, for the most part, kind of get in the way. And what I mean by that is if we took our water and we threw a little salt in it, some sodium chloride. So we have some water molecules there, but now with the presence of the sodium chloride, I'll represent that by kind of blue circles. So we have some blue sodium chloride in there. What happens is we now have a lot more particles sort of floating around in the solution. And what this does, for example, is it gets in the way, frankly, of these water molecules. Let's just say you want to heat this thing up. It gets in the way of these water molecules trying to escape, right? It's got to go around all these sort of extra stuff floating around in the solution to try to escape. The result of that is obviously over here, it's kind of more of a direct run out of the solution. So this process, right, is like I got to take the long way around, which, like, if you think about it with gas, going to take a lot more gas to get around, right, the neighborhood, if you're trying to take the long way versus the straight way. And the result of that is it's going to take a lot more energy for it to sort of escape because it's got to travel through all these other particles that are in its way, basically. The result of that, for example, as we will see, is when you dissolve a some type of substance in water. When you go to boil it, the boiling point will actually elevate because it will take a lot more energy to get it to escape. The result of that is the boiling point of the solution versus the boiling point of the solvent or the water will actually be higher. So it actually takes longer. Same thing sort of happens in this situation as well. Um, if you put in some salt in here, and in this guy where we want to kind of maybe freeze it or something like that and remove energy, again, the water molecules got to kind of go around all that stuff to try to come together. The result of that is it's going to have to remove a lot more energy, and we're going to see actually a lower freezing point. So things where you make solutions and you dissolve solute in a solvent will change things like the vapor pressure of a solution. It will also change things like boiling points of a solution or the freezing points of a solution. And the effect of that is affected by really the number of particles there is. Usually the more particles there are sort of in that solution that's been dissolved, the greater the effect on things like freezing point, boiling point, and vapor pressure. Questions on that there? So the first sort of effect we're going to talk about is vapor pressure lowering. And remember that the vapor pressure is really the pressure exerted by the gas molecules that escape basically the liquid phase. And those gas molecules are sitting above the liquid. And obviously, because they are in the gas phase, they have pressure, and that is what is known as the vapor pressure. So the result of basically having particles dissolved in a solution will result in the vapor pressure of that solution basically lowering. So the vapor pressure of a solution depends on the nature of the substance and the temperature. When you add a substance, the vapor pressure is lowered because, again, the molecules in the substance cannot evaporate to the surface as easily as they could with the absence of those things. So it kind of goes back to what I kind of drew a second ago. Again, in like pure water, water molecules have kind of like a clear path to escape, basically. In a solution where you have something again dissolved, these water molecules again run into some roadblocks along the way as they are basically trying to boil and escape the solution. So again, they got all these other things in the way, and it's going to take a lot longer for them to do so. Because it takes a lot longer for them to do so, that means less gas molecules are going to escape above the solution, and less gas molecules above the solution will result in a lower vapor pressure because there's less gas molecules basically above the solution in that case. So there is a law here, which is known as Raoult's law, and it deals with vapor pressure, and it is the pressure of a component is equal to the mole fraction of a component times the vapor pressure of really the solvent by itself or the pure substance by itself. So this is kind of the vapor pressure of the solution. That is the mole fraction that we just talked about. And this is really the pure substance vapor pressure like the solvent's vapor pressure. The vapor pressure lowering can be defined as the vapor pressure of the pure substance minus the vapor pressure of the solution. That is because it is a lowering, which means the solution will have a lower vapor pressure than the solvent, for example, by itself. So this number here will be a larger number. This will be a smaller number, and that will give you a positive sort of change in the vapor pressure. So again, the result of these particles in there will basically prevent the gas molecules from escaping, resulting in a lower amount of gas molecules up on top, and again, a lower vapor pressure. So let's take a look at one here. Why don't you take a second here and try it? The vapor pressure of ethyl alcohol is 66.5. Calculate the vapor pressure of ethyl alcohol in a solution that is made up of 0.2 moles of glucose dissolved in 1.25 moles of the ethyl alcohol, basically. Okay, so let's take a look. So in this particular case, we have a solution of ethyl alcohol, and dissolved in there, you put some glucose in it. So you got this kind of glucose ethyl alcohol mixture. And we want to know what is the vapor pressure of the ethyl alcohol in it. And we could do that by taking the pressure of our ethyl alcohol equals our mole fraction of our ethyl alcohol times the vapor pressure of the ethyl alcohol by itself. So in this particular case, our mole fraction will be the moles of our ethyl alcohol, which in this case is 1.25, divided by, again, our total moles, which is 0.2 for the glucose and 1.25 for our ethyl alcohol. So here we will end up with 1.25 divided by 0.2 plus 1.25. Going to get us 0.862. Call it 1. And now we can put it in here, the vapor pressure of our ethyl alcohol will equal our 0.8621 times our 66.5 torr. And when we do that here, we will end up with 57.3 torr as our vapor pressure of the solution, the vapor pressure of ethyl alcohol in the solution is the way to say that. We do see that the vapor pressure of ethyl alcohol pure by itself was 66.5. With the presence of glucose in there, it drops the pressure of the ethyl alcohol to 57.3, which is, again, the vapor pressure lowering part of it. Now, when we talk about glucose in this particular case, glucose is a non-ionic, right, solute. What does that mean? Glucose is basically carbons, hydrogens, oxygens, which means when you take a glucose sort of molecule and you put it in to dissolve, you basically get one glucose molecule that will dissolve. It will not break apart, right? So it will stay together as it is covalently bonded, right? So even though it will dissolve because it's covalently bonded, it will not break into ions, right? Ions, as we will talk about in a bit, are a little bit different in terms of its colligative properties, because when ions go into a solution, they break apart into multiple different numbers of ions. So because glucose is a non-ionic solute, or any solute that is basically not going to break apart into multiple ions, we do not have to sort of take into account, for example, how many ions are going to be in there. In terms of the colligative property, which in further cases we do when it is ionic, because it may produce more than one sort of particle per solution. And because colligative properties are based on the number of particles there are, that will also affect actually the outcome of it. Now, let's just say, for example, that we knew the vapor pressure of glucose under normal circumstances, this sort of same situation. And let's just say it was, I don't know, I'll make it up here. Let's just say it was 24.9. We'll go with, why not? Let's just say for randomness here that it was 24.9 torr was the vapor pressure of glucose under the same conditions here. Now, we could also do the mole fraction for glucose the same way. We would then do, obviously, glucose's moles, which would be 0.2 divided by 0.2 plus 1.25 moles. And that would give us, obviously, we could also subtract from 1, about 20%, I think. 0.1379. And if we now take that times our vapor pressure there of pure glucose there under these same conditions, we could get the vapor pressure of glucose in the solution, which would be 0.1379 times my 24.9 torr. And if we do that there, 0.1379 times 24.9, in that particular solution, the vapor pressure of glucose would be 3.43 torr in this case. So the reason I'm saying this, by the way, we also see a vapor pressure lowering, right, for glucose, right? And there's a lot of ethyl alcohol, right? A lot more moles of ethyl alcohol in there. So we see a much greater amount of vapor pressure lowering, for example, in glucose than we did, say, in the ethyl alcohol, right? Now, if this was sort of an ideal solution means kind of like the ideal gas law in ideal conditions. When we have partial pressures, we could actually figure out the pressure of the solution in this case by taking the partial pressure of ethyl alcohol with our partial pressure of our glucose in this case. And overall, this solution would have a overall sort of vapor pressure of about 60.7 torr if we added this number and this number together. So you can obviously figure out sort of the vapor pressure of both components within a solution if it's a sort of an ideal solution. And you could add both of those vapor pressures together for each of the components, and that will give you technically the overall sort of vapor pressure of that particular solution based on those components that are within there. Any questions on either of that? Yeah. You can, as long as both of those pressures, obviously both pressures would need to be the same unit if you're trying to figure out something like a mole fraction. But whatever the unit for the vapor pressure would be is probably what you'll end up, obviously, with the unit when you solve it for the component of it. But you can use any one. You can use atmospheres, millimeters, mercury, torr, and all that. Yeah. Other questions? So again, the presence of these extra particles in the solutions prevents sort of the easiness of those guys to escape the liquid phase and go into the gas phase. The result of that is, again, we're going to get less of them escaping the liquid phase into the vapor phase. And because we will have less of those guys, we will see a lowering of the overall vapor pressure because there's less gas molecules above the liquid. All right, that's the guy we just did. The next sort of aspect of a solution that we're going to look at in terms of as affected by these colligative properties is actually freezing point. And with freezing point, the way that a, say, solvent, for example, is affected by the presence of these extra solute particles within the solution is they interfere with that process, again, of everybody coming together in nice ordered fashion. Again, you could think of it just kind of oversimplified as, with nobody involved, there's going to be really no problem for these guys to get close to another and sort of come together and basically freeze themselves in a nice ordered pattern. Again, with the presence of other things in that solution, like solute particles, you just kind of get in the way of those guys being able to just naturally kind of come together as the energy is being released. The result of that is we will actually see the freezing point of the solution decrease and go down. So it actually freeze at a lower temperature than the solvent would normally freeze. And that is the freezing point, and this is the equation for the change in freezing point temperature is equal to Kf times M. This is not, and very often confused by people, when you solve for this, this is actually just the change in the freezing point temperature. And usually, I'll be honest with you, it is usually in degrees Celsius. And that is because this is a constant. This is what is known as the freezing point constant. And the freezing point constant is something that you could look up in the table. Now, it's really important when you go to that table to look up the freezing point constant. The freezing point constant is not the solution. So a lot of times people will go to those tables and go, I cannot find like the solution in the table. It is based on the solvent. So you got to figure out in that solution, what is the solvent? And that is what you want to go to the table and look up. So for example, if it's an ionic compound, probably in a lot of cases, the solvent will be water. If it's some type of aqueous solution, probably again, in most cases, will be water, but it will not always be water in a lot of these problems. So you just got to make sure you know what the solvent is. That's also important as well, knowing when you find out what the solvent is, to know the normal freezing point, the temperature at where it freezes. For example, water is 0 degrees Celsius, right? When we talk about water freezing, its normal freezing point is 0 degrees Celsius. If by some chance you have a problem where the solvent is not water, it is some other substance, it may have a different freezing point than 0 degrees. So you got to make sure that you figure out what that is. The good news is usually in that table where you find the constant, the Kf constant, they oftentimes will have the normal freezing point of that solvent with it. So a lot of times they'll be in the same table. So a lot of times you can find that information pretty easily. Now the M here is our molality, not molarity. So this is our moles per kilogram of solvent. So that is our molality in this particular case. Now, because the freezing point temperature actually decreases, it gets smaller than where it started. When you think about the change in freezing point temperature in this case, you want to take the temperature of the pure solvent by itself, because it should be a higher value, minus the temperature of the solution. So this is really important because this is really where you will be able to figure out what is the temperature the solution actually freezes by solving for this guy. So if you do solvent minus solution, what that will do is allow you to either add or subtract correctly, just by solving for what you have in this equation. So you want to make sure you go sort of the correct way. So for freezing point depression, we want to go solvent, which is a higher number, minus the solution, which is a lower number. So typically all these sort of colligative properties, when you're looking at what the change in pressure, change in temperature, you usually want to always take kind of like the larger number, what it should be the larger number minus the smaller number, and that will give you sort of the correct math when you go to solve for the solution, for example. So this equation here is for non-ionic solutes. And the reasons for non-ionic solutes is kind of like glucose, what we just talked about. When you have something that's a non-ionic guy, when you dissolve that in a solution like water or a solvent like water, you get a 1-for-1 relationship. So when you dissolve that solute, You only get one particle for every one that you dissolve in there. So later on, when we get to ionic guys, we will put something right about there. But here, basically, it's one, so there is nothing there for these type of solutes. So if the solutes, again, are non-ionic, we basically don't have to worry about multiple particles coming into the solution at once, because again, when you throw in something like glucose or some non-ionic guy, it is a one-to-one relationship. For every one that you dissolve, you get one particle that's floating around in the solution. Another effect on solution when you have things in there, as we talked about with vapor pressure lowering, and also before that, is the boiling point. The boiling point will actually be elevated. And again, with the presence of these particles, as we talked about, it takes a lot more energy to sort of get around all the particles that are floating around in the solution. The result of that is going to take a lot more energy for the solution to boil. You have to put more energy in there to get it to boil. And the result of that is it will actually boil at a higher temperature than it started with. And in this case, we have a very similar equation to the one we just saw. This is the change in temperature of the boiling point is equal to Kb times m. That is the, again, change in boiling point temperature. Once again, not the temperature that it boils, but the actual change in the temperature in degrees Celsius. This again is the boiling point constant, and that is a value you look up in a table. Just like the previous one, it is based on the solvent as well. And once again, here our M is our molality, which is our moles per kilogram. This also is for non-ionic compounds. Same reason. It's a one-to-one relationship, so we don't have to worry about anything here. The difference here, though, is the solution here will actually boil at a higher temperature than the solvent. So in this case, when we talk about the change in the boiling point temperature, we actually take the temperature of the solution where it boils, and we subtract it from the temperature of where the pure solvent boils. Now, again, if we're talking about water, which you very often are in terms of the solvent, we should know that water normally boils at 100 degrees Celsius, right? That is the normal boiling point there of water. Once again, if water is not your solvent, you will have a different Kb value, and you might have a different temperature at which it boils. Any questions on that there? By the way, that is like why you add antifreeze to your car. Antifreeze actually does both things. It lowers the freezing point of your car's water, and it increases the boiling point of it. In case you live in a really cold environment, your water and all that doesn't freeze unless you get a really cold temperature. And it also increases the boiling point in case you live in a really hot environment. Your car won't overboil for that. So when you put antifreeze in your car or coolant, that is basically, it actually has the ability to do both things, actually lower the freezing point and increase the boiling point, and allows, again, hopefully your car not to be boil over or anything like that. All right, so let's take a look at some of these here. Here is, by the way, again, a table of constants, and you have a similar table in your book. And you can see a couple of things as we talked about. These are all based on solvent here. And the different solvents do have different freezing points and boiling points. So again, it's important that if it is not water, you don't use 0 and 100. But if it is water, 0 and 100 is the number that you use. 1.86 is the freezing point constant, and 0.512 is the boiling point constant there for water, which is a solvent. Once again, though, if you had something like diethyl ether, you can see the freezing points minus 116 and 34.6, and also different values for the Kf and Kb. So obviously these would be provided for you. But again, if you're looking them up in tables, you want to make sure that you do find the solvent. You will not find the solution on here. It is based on the solvent. So let's try one here. What is the freezing point temperature of a 1.7 molar aqueous ethylene glycol solution. So take a moment and see what you come up with. Let's take a look. So obviously this is freezing point. So we're going to use our freezing point equation, which is the change in freezing point temperature is equal to Kf times M. Again, here, this is non-ionic. So we don't really have to worry about multiple particles for each of these things to dissolve because it's covalently bonded. It is a one-to-one situation, as when it dissolves, one particle of that will produce one particle in the solution. And again, that's important because colligative properties are really all based on the number of particles that are in the solution. So because of that, we will use this equation like we need. We are actually given the molality. In some cases, you do need to actually calculate the molality yourself. So again, you might need to calculate the molality of it. We will look up the Kf value on that table. And the key here, it does say aqueous. So usually in this situation, if it doesn't really specify something other than water and it does say aqueous, you could probably safely assume that water is going to be your solvent. So again, that is why we would look that up. We also know that the normal freezing point of water is 0 degrees Celsius, right? So when we do this, the change in the freezing point temperature will equal our 1.86 degrees Celsius times the molality. And again, since they did give us the molality, we did not need to calculate it. And that will give us here 1.86 times 1.7, which will give us something like 3.162 degrees Celsius. Just so we're clear, is that the answer? That is not the answer, by the way, even though a lot of people might put a box around it at this point. If that was the answer, that would mean that my freezing point actually went up, right? Because it normally freezes at 0. And if it ended at 3.1, that definitely went up, which is not depression, which means it goes down. This is why it's important to remember that the change in freezing point temperature in this case is the temperature where the solvent will normally freeze minus the temperature of the solution. So what we just calculated is this guy, 3.162 degrees Celsius. Our solvent normally freezes at 0 degrees, which is what water is, minus the temperature of the solution. We're going to subtract this to this side, subtract that back to that side, which means the temperature of our solution will actually freeze at minus 3.162 degrees Celsius. So the temperature of our solution is equal to 0 degrees minus 3.162 degrees Celsius. And that's really important. So that's what I was talking about earlier, that understanding the change in freezing point temperature or the change in the boiling point temperature, either taking solvent minus solution or solution minus solvent will give you the correct sign in this case. Now that makes sense because that is a freezing point depression, right? You basically, normally water will freeze at 0 degrees because of all the particles in there. You got to get it down to minus 3.16 degrees. You have to release a lot more energy to get all those particles sort of out of the way for it to freeze. Any questions on that there? Okay. All right, let's see. That is that one there. Why don't we try this one? Let's calculate the molar mass, which is grams per mole, right, of a compound that is of a solution that's made up of 12.0 grams dissolved in 80 grams of water, and this solution freezes at minus 1.94 degrees. And again, this is going to be a non-ionic solid that we're dissolving in there. So take a moment and see what you come up with. So let's take a look. We got, well, I calculate the molar mass, which obviously is grams per mole, which is what molar mass means. So I'll change the page. We have 12 grams of this substance that we're trying to figure out the molar mass of. So actually, we do have the top part there, which is 12. It's dissolved in 80 grams of water. We know that that's the solute because 80 grams obviously is more, and that water means that the mass of our solvent is 80 grams. It freezes, so the temperature at which the solution freezes is minus 1.94 degrees Celsius. And obviously, we know that the solvent is water. So we do know that the Kf that we would look up on the table there is 1.86. And we know that normally water will freeze at 0 degrees Celsius. So we could use our freezing point equation here to help us figure out a few things. So let's see here. The change in freezing point temperature is equal to our Kf times our molality. This molality is moles per kilogram of solvent. And by the way, that is the only thing that has moles in it. And that is where the moles is going to eventually come from, is from the molality part of the formula. So we're going to use our freezing point equation here to figure out the molality. And then using the molality and the amount of the solvent will allow us to get to the moles part of it. So also a very common mistake is, once again, this is not this. Again, that is the temperature at which this solution freezes. So the change in the freezing point temperature would be the temperature of the solvent minus the temperature of the solution. We know that the solvent is 0 degrees Celsius where it normally freezes, minus our minus 1.94 degrees Celsius gives us a positive 1.94 degrees Celsius. So if you're curious of how the negative goes away, that is how the negative goes away. It should go away because the change here is basically 1.94 degrees Celsius. So now that we have the proper change without the negative there, that will equal our Kf, which is 1.86 degrees Celsius molality times our molality. We're going to divide this to the other side. That will give us 1.94 divided by 1.86. Going to give us a molality in this case of 1.04. Remember, that is moles per kilogram of solvent. Any questions on that part so far? That's okay because I do know the mass of my solvent, right, which is 80 grams, but I do need to convert this into kilograms, right? So I'm going to take my 80 grams. There is 1,000 grams in a kilogram, and that's going to give me 0.08 kilograms for my solvent. I could use that by now timesing my molality I just got by that number, 0.08 kilograms of my solvent will now cancel. And that will leave me the moles of my solute in this case, which is 0.08344, we'll call it. That is the bottom part here of the molar mass that we need. Any questions on that there? So really in this particular case, we're kind of just using the freezing point equation to get to the moles of the solute. And now we could actually calculate the molar mass of this substance by taking the grams, which was given to us, 12 grams, divided by the moles we just calculated. And that's going to give us a molar mass in this case of, we'll call it about 144 grams per mole. Question on that. So there is a lot of applications sometimes where we find things like molar mass. Obviously, we can find the temperature which it freezes by knowing the sort of this freezing point information, as well as if it's boiling point, we could do obviously very similar calculations. Any questions on any of that there? All right, then let's take a look at another one here. Just one we just did. All right, try this one here. How many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that boils at 105 degrees Celsius? The Kb value for water is 0.512 degrees Celsius over molality. All right, so take a moment. We're looking for how many grams of this guy. So carbon is 12.01, hydrogen 1.008, and oxygen is 16 here. To look, once again, a couple of things obviously important as you read through this. We want to know how many grams of ethylene glycol, which is really our solute. And again, this is non-ionic so we don't have to worry about multiple particles happening here. We have a kilogram of water, which is our solvent in this particular case, so hence why we look this up. This is boiling, which means the temperature at where this water normally boils should be 100 degrees Celsius. We also could use our boiling point temperature equation here. And in this case, we see that the solution here will boil at 105 degrees Celsius. So putting this into this equation, we once again want to make sure that we put in the change in boiling point temperature, not the temperature where it boils. So once again here, this is boiling point elevation, which means the solution will actually boil higher than the solvent. So we will take the solution minus the solvent here. So the solution is 105 degrees Celsius. Water normally boils at 100 degrees Celsius, which means we are looking at a 5 degrees Celsius difference here for our change in boiling point. So again, it's really important that you use the change in boiling point temperature in this equation. Uh, if it's boiling point, you probably won't get as lucky as you would if it's freezing point, because freezing point is 0, which means you'll probably have the same number, just the sign will be wrong. But here you definitely will be off by a good factor if you use the temperature at which it boils. So with that being said, we'll pop in there our 5 degrees Celsius, our KB, which is 0.512 degrees Celsius molality. This is going to be times our molality. We're going to divide this to the other side, and that will give us 5 divided by 0.512. That's going to give us a molality of 9.7. I feel like there's a 7 in there I missed there. I got 9 point, we'll call it 766. We'll go. And that again is going to be moles per kilogram of solvent. In this particular case, our solvent's already in kilograms, which is 1. So we can multiply this by 1 kilogram. The kilograms will cancel. And basically that will give us 9.766 moles of our solute, which in this case is C2H6O2. C2H6O2. Obviously, at this point, it's just a conversion from moles to grams using the molar mass from the periodic table. So that is 2 carbons at 12.01 plus 6 hydrogens at 1.008 and a couple of oxygens at 16 each. Gives us 6207 as the molar mass. So using that obviously as a conversion factor, 9.766 moles. We want moles on the bottom here. So the 62.07 grams per mole will go like so. And that is going to get us here 9.766. Looks like about 606 grams of this guy needs to be dissolved. Yeah. Any questions on that there? So you can see you could do a similar sort of calculation. You can figure out how many grams of a solute you need to dissolve. You also could do like a molar mass type situation, or again, where it actually will boil. Any questions on any of that there? All right, so that's the one we just did. All right, so once you do this one, calculate the boiling point in degrees Celsius of a solution that's made by dissolving 1 gram of glycerin in 54 grams of water. And again, the KB here for water, 0.512. And our molar masses, like we just used in the previous problem, 12.01, 1.008, and a 16. Okay, so let's take a look at this one. Obviously, again, we're dealing with boiling point in this case, so we'll go with our boiling point formula. Once again, here we are dissolving a non-ionic guy, so it's a 1-to-1 relationship, so we're good. We are looking for the actual temperature at which it boils, and we have our solvent here. So we do, in this case, need to actually calculate the molality, which is our moles of solute over kilograms of solvent, as it is not given to us, but it is, but just some parts. So to do that, we do need to convert our 1 gram of glycerol, which was C3H8O3. C3H8O3. We obviously will need the molar mass from the periodic table to do that. So that's going to be 3 times 12.01 for the carbons, 8 times 1.008 for the hydrogens, and a 3 times 16 there for the oxygens. Going to give us here 9209 grams per mole from the periodic table. And that will give us 1 divided by 92.09. Going to give us 0.010859 moles. Now, this water obviously is our solvent, which is why, again, we looked it up on the table. And we also know that normally the temperature where this guy boils is 100 degrees Celsius. So we do need to convert our solvent into kilograms so that we do get the molality. And again, that would be obviously 54 grams of water, and 1,000 grams of water is 1 kilogram, giving us 0.054 kilograms. We now have everything we need to solve for the molality, which would be 0.010859 moles divided by 0.054 kilograms. And that's going to get us there 0.054. It looks like 0.20109. And again, keys both units are just a little m. We now have everything we need on this side of the equation. So going into our change in boiling point temperature, our KB from the table, 0.512 degrees Celsius molality, times our molality that we just calculated, 0.20109. Molality will cancel, going to give us degrees Celsius, and we will end up with 0.10 degrees Celsius. Once again, though, that is not the answer here, right? So that is the change in boiling point temperature. So remember that the change in boiling point temperature is equal to the temperature of the solution minus the temperature of the solvent. That means in this particular case, 0.1 degrees Celsius equals the temperature of the solution minus where water normally boils, which is 100 degrees Celsius. Adding that to the other side gives us a whopping 100.1 degrees Celsius is where this solution is going to boil. It did go up a little bit from the solvent by itself. Any questions on that? So again, sometimes people, when they solve for that change in temperature, either freezing or boiling point, they kind of box that as the answer for the actual temperature where it freezes or boils. So you got to make sure that you do that adjustment. Like I said, with the freezing point one, if it's water, you'll have the right number, but probably the wrong sign. But if it's boiling point, you're going to be way off because you're going to be off by that 100 difference and stuff like that. Questions on that there? All right, we'll lay it up there.